we're going to move to the first section of this course. So we'll talk about the background. Okay, let's first take a look at the energy resources in the U.S. So by energy resources, we focus on the resources which can generate electricity. Although this course is talking about the general power system analysis regarding dynamic problem, but we have to utilize the U.S. power grid as the basis to develop our analysis modeling. And if we need to relate any material into a real problem, we always use U.S. power grids. So let's start from the energy resources in the U.S. So in this chart, it just shows different type of resources, including the hydro, nuclear, wind, solar, coal, fossil gas, and maybe other type of resources you can generate electricity. So for a long time, the coal has been dominant resources. Let me bring my laser out. Does anyone see my mouse?
Yeah,
down on the bottom left.
That's good. That's fine. So yeah, over a long time, the coal-fired power plant have been the major generation of the entire U.S. Then you see around maybe 2005, and the U.S. power grid start retiring the coal-fired power plant, and that is replaced by fossil gas, pretty much natural gas, combustion turbine power plants. Because natural gas power plant, although they're not clean, not one clean, but it's a cleaner than the coal-fired power plant. If I correctly, the CO2 emission from natural gas pretty much maybe only just a half of the coal-fired power plant, or even less. And when they start retiring the coal-fired power plant, and the renewable also grow up, you see the solar and the wind actually grow starting from around 2005. And the nuclear stayed pretty much flat because after 2000, and it's hard to prove any new nuclear power plant. Although some engineers believe nuclear power plant are pretty clean, right? They should be considered clean energy resources, but the public, not every one of the public agree. But maybe someone just believe as long as it's not in my backyard, it will be considered clean energy. Yeah, so nuclear is pretty flat. The hydro is really flat because by in the past 20 or 30 years, pretty much all the potential hydro power has been utilized. So it's very hard to build any new hydro power plant. So when the coal-fired power plant is retired, the natural gas pick up, and the renewable is going up. So, and you see the total load stay flat. Why? Because there are many generations actually move to the consumer level, and also the energy efficiency emphasized. So they can achieve about the same total demand of the U.S. grid, which is good for us to do analysis, because if you try to estimate how much generation we need to have each year, what is the total power we need to generate, so you pretty much can use the data like 10 years old data. So the total generation is still about the same. I couldn't find a figure for the past 4 years, but I assume they're pretty same. Okay, so this pie chart is the first pie chart I used when I taught this the 522 the first time back to 2012. So so at that time you see the coal-fired power plant is the #1 electricity generation resource. It takes 42% of the electricity, which is generated by coal-fired power plant. The #2 is the natural gas, take 25%. The nuclear take 19%. Hydro take 7%. So these are other renewables. Other renewable means any renewable excluding hydro. Okay, because hydro is also considered renewable, but definitely that's considered not new renewable. It's different from this first chart. The first chart, it does show the solar and wind individually. So this other renewable means like a wave power or any other one, which are renewable but not solar or wind. Okay, so this green one does include solar and wind. So that 14 years ago, it only just take 5% of the total electricity generation. So this is the chart in 2023. So you see now the coal-fired power plant has dropped to only 16%. So it's lower than natural gas, lower than nuclear, and even lower than the solar and the wind together. So the coal, there's still some coal-fired power plant, but they're not the major, the top resources of electric generation. So why do I show this chart? I just want to show how the combination of electricity generation resources change over years. And I may ask you some maybe quite quiz question about what is the number one? What is today's number one energy resource? So the answer is natural gas. What is the number two, which is nuclear? What is number three, which is coal? So that answer can change over years, okay? In this slide, I'm going to show three pictures. The first picture about where the electricity is utilized. That is very, or maybe more accurately speaking, where the electricity is utilized in evening. Actually, yeah, because this really covers many time zones. Anyway, so this is the US map or North American map seen from the outer space. You can see where you see a lot of lights, which indicate a lot of people using electricity. So the lights are dense, very dense in the eastern side, but not, and in the middle west, that's pretty empty. And on the west coast, there are also a lot of electricity users. The second picture shows the transmission grid. So that matched pretty well with the first picture, because on the eastern side you have very dense transmission grid, and in the middle, in the Midwest area, that's a pretty sparse, and on the west coast you also have a denser transmission grid. The third picture shows the type of energy resources by using different colors. So the map intentionally just used like dark gray to indicate coal-fired power plant, which is means not very clean energy, and use like a green or yellow indicate wind, solar, which are clean energy, like natural gas or nuclear, some color in between. But from this map you can tell. So coal-fired power plant is distributed widely through this entire country. Hydro power plant, which is a blue color, pretty much near the border between the US and Canada, near the lake, rivers. And in Tennessee, you see, because we have a Tennessee River, we also have some large hydro power plant. For instance, one of the largest hydro plant near Knoxville is the Norris Dam, which is actually the first project of TVA. And so for the wind, if we try to find out the wind power, so which is pretty much in the Midwest area of the country. But if you compare this figure versus the first one, you see there are not many users there, right? So if you generate a lot of wind power, you need to deliver either to the East Coast or to the West Coast. And the solar is similar. Solar pretty much in the Southwest region, in California, in Arizona, in Nevada state. But there's some also there, but there's some interesting things. Even in some like northeastern region, you have a lot of solar. So solar doesn't depend on how much solar resource irradiation you have. It's pretty much based on also depend on incentive the state government to provide for the user to install their solar. Okay. So for this course, we're not going to talk about the detailed principle of a wind generator or solar farm, but we do want to talk about some stability or reliability concerns due to the integration of wind power and solar power. This slide we talk about the wind power. Okay, so this map used the blue color to indicate where the wind power is pretty rich, which means you can build large-scale wind farm to generate electricity from wind. They also use the red color to indicate where people live, right? So, which means you can you need to utilize electricity. So if you can do like a simple math to integrate the total generation by wind and the total electricity need by people, even those two numbers are close, you cannot fully rely on the wind generation because you need to have very strong transmission grid to deliver the wind energy to the cities, right, to the users. Otherwise, you cannot get electricity. So the first, number one, you need to build a very strong transmission grid. Then the second picture just show the curve talking about the load change for 24 hours of one day, and also the generation of the from wind changing one day. You can see the curve not matched. So the load will have the maximum from maybe 2 o'clock to from 2 o'clock to 9 o'clock, from the late afternoon until the early evening. So that is the peak hours for electricity. And off-peak hour will be the early morning from 1 o'clock until maybe 6 or 7, okay, before people wake up. But if you check the curve for the wind is very strong in the early morning, but it's weaker in the late afternoon. So which means even the integration, if you integrate the curve for the area under the curve, the integration tell you the total area for the electricity generated from wind is equal to the total electricity you need for people. Even those two numbers are same, but they still have mismatch, the temporal mismatch. So you need to figure out a way how you can save the energy generated in the early morning and maybe by battery or by any storage and deliver to the user in the afternoon. So there are also some mismatch. So this example reminds us when we talk about reliabilities, we cannot just use very simple math. We cannot just calculate, okay, before my system can generate this much energy and my system needs that much energy. So if the first number is bigger, so I'm safe. No, that's wrong. So you need to make sure at any moment the power is balanced between the generation and load. That's very important. Otherwise, your network, some violation will happen and some equipment will be tripped. So although the potential of the wind generation can support the total load, but there could be some geographical or temporal mismatches in supply demand, which need to be addressed. So that's the number one concern brought by the integration of wind power. The number two concern is about the uncertainties. So the bottom chart indicate in the same month for the same location, and if you try to draw the wind generation by the same wind turbine wind farm at the same location, so you can see the curve are very different for different days, which means do the forecasting for the wind generation is also a challenging problem. So the wind generation will bring a lot of uncertainty. So it's different from like a fossil fuel generator. For fossil fuel generator, you can control how much fuel you are going to feed to the turbine, right? To generate electricity. But for the wind generation, the generation pretty much depend on the power, the wind. So the wind go up or go down, that will influence the generation. The number 3 concern is about the decrease the system inertia and the frequency response. So if you're going to retire like a coal-fired power plant, because those are pretty dirty, you want clean energy. So if you retire maybe 500 megawatt coal-fired power plant and replaced by a wind farm, which can generate 500 megawatt power, even let's say we are talking about one city which is in the wind-rich area, right? So we don't need long distance power delivery of electricity from this wind farm to the user. We can just use the power locally. And also we have pretty, and in that area, we have a very good energy storage. We can save energy. We have no concern for second charge. And for third charge, we have very good forecasting. Okay, but you still have another concern, which can cause some reliability violation, which is about the frequency response. So when you have a coal-fired power plant, because coal-fired power plant has very large rotor and which has inertia, which means if you have disturbance near that power plant, the rotor will take some time to speed up, to decrease the speed. If you, for example, if you suddenly just lose a load, okay, the frequency will go up. If you suddenly trip another generator, the frequency will go down. The frequency change will not be fast if you have inertia. But when you replace the conventional generation by wind power generator, so those generator has lower inertia or have no inertia. So if you have a fully power electronics inverter to connect the wind turbine generator to the grid, so inertia will not be added to the transmission grid. So when the inertia decrease, the frequency will drop much faster. So after disturbance, the system frequency will go through 3 stages. First will decline at a certain speed. This speed only depends on system inertia. So if the system inertia is large, this slope will become very shallow, will be much smaller. So it will take a longer time to decline the frequency. But if the inertia is very small, it will quickly drop to very low frequency, and that can trigger some frequency protection. And the governor of the generator only become active after maybe a couple of seconds, because each governor has some dead band. It will take 1 or 2 seconds to start bringing the frequency back, and then we can utilize AGC, which will be maybe 10 seconds later. Okay, so even you have very strong governor and very strong automatic generation control, you still cannot guarantee the frequency decrease to very low value. So that only depends on inertia. So when you replace the conventional generators with large inertia by wind turbine generator or by solar farm, so inertia will become smaller. So the frequency can be more easily violating the reliability criteria. So those are all the concerns. Okay, so which means there will be additional costs for either upgrading transmission to prevent the congestion or installing the energy storage or batteries and expanding reserve for to balance the change of the load. All this means wind power is not free. Okay, the wind is free, but wind power is not free. Okay, so second slide, we talk about the solar power. So the integration of solar power at large scale also brings some reliability concerns. So one major concern is called the dark curve or dark chart in California. Because California has a goal to reach 50% of clean energy or renewable by 2030. Okay, so this dark curve was generated around the time of 2015 or 2016, based on their load curve from 2012. Then they draw the load curve 2013 and 2014. Then they realize, okay, so for the curve, especially during the time from probably 7 or 8 a.m. and 6 p.m., the curve will change significantly. Okay, so that is pretty much the time from the sunrise to sunset. Okay, when the solar farms start generating electricity. Because there's a lot of like rooftop solar panels, they are generating electricity for the consumer to use electricity locally. So that actually take part of the load curve. So the more solar power integrated, so the curve during this time frame will become lower. So it become deeper and deeper until, based on their prediction, by 2020. So now it's 2024, right? Pretty much the prediction is pretty accurate. So they will have this load curve. Remember, in the past, usually the peak hour happened from the late afternoon until maybe 7 or 8 o'clock. But right now, the peak load will happen after the sunset, and there's a very large dip from 7 o'clock from in the daytime. Okay, so you may say, okay, it's not bad at all, because if I integrate how much energy I need to generate it from the major power plant, because this part of energy is generated by user from this rooftop solar panels, and my power plant from the power company will only just need to generate this much of energy, right? I need to generate less energy, but as I said, you cannot do simple math, right? We have to make sure the generation can meet the load for every hour, for every minute, or every second. What happened is this generate a curve which is pretty like the dark, right? The dark stomach, and will make this part be very deep. Will create 2 times. The first time is the load, the generation need to decline very quickly from maybe 7 or 8 o'clock, right? At the very last load. And around 3 p.m., it need to increase also very deeply to the peak load. So that brings some challenge for the operator to operate the power plant. So if you do this math, so this ramping speed is about 13 gigawatt load in 3 hours. So you need to increase the generation in California by 13 gigawatt load. That is pretty challenging for conventional power plant. Because based on the data, if we were talking about, if we want to, okay, let's say we have some gas turbine, we have some conventional generator, and we need to wait until like 3 p.m. Okay, when this time starts, we immediately start those power plant and we start ramping the generation up. But this speed can be higher than the average speed of a conventional power plant. Because the average ramping rate for the gas turbine generator, the gas turbine generator has been the very has been considered with very fast response. The gas turbine generator can increase the generation by about like 1.5 gigawatt per hour, which means for 3 hours, it can only just increase by about 5 gigawatt, which is still less than this value. So how are you going to address this problem? You need to have a lot of energy storage, because energy storage can respond much faster than the conventional generator. You need to have energy storage, or you can have a lot of spending reserve. By spending reserve, which means they are conventional generators, they're running all the time, but they're not generating electricity. So when you need their power, they will just increase their generation immediately. When which means you still keep those generator in the grid. Okay. So this can bring some risk with the balance between the generation and load, especially during the daytime. Definitely, this can also cause some decrease of inertia, because if you replace the conventional generation by the solar farm, your inertia will be also decreased. Okay, solar power is not free. Even the sunlight is free, but solar power is not free. Before this lecture, I found this picture which show what today's California system look like. Basically, what the dark curve is look like. It's actually getting deeper, right? If you see, it show the curve. This black curve is actually about 23. In the daytime, at around 2 o'clock. So the net generation you need from the transmission grid, it can be decreased to almost 0 or even negative. Okay. So which means if you don't have enough energy storage, pretty much you need to stop all the conventional generator, right? Because you have net generator. Definitely, the California is connected to other state, other transmission grid. So you need to send electricity to other neighbors in order to balance the entire system. Is there any question? Okay. By the previous 2 slides, I just show what we are going to discuss by this class. We are going to address some stability control problem for power system. Even for this course, we're not specifically talk about the principle of a renewable, but we do want to cover the impact due to the integration of renewable. This slide shows the AC power system structure, including generation, transmission, subtransmission, and diffusion systems. If we draw this very simple power system starting from one power plant to generate electricity and to deliver over long distance through transformers, transmission lines, and to the end users, this is literally speaking a whole power system. And we can partition the system into 4 sections. So we can include the generators into the power plant together with some transformer as the section of generation. So usually this part of system is operated at a lower voltage. So by lower voltage, I'm not talking about like 130 volt. So it's 23 kV, which is lower than transmission voltage level, because the generators, in order to maintain the low cost of the manufacturing and maintenance, we don't want to increase the installation cost. So it's better to operate at a voltage much lower than transmission voltage. So usually it's lower than 25 kV. Once the electricity generated, it will be delivered through high voltage transmission, through the transmission, long transmission lines and tower. And we need to have a step-up transformer to increase the voltage to transmission level. So you may go through a number of transformer until reaching very high voltage. So for transmission system, which is the backbone system of the entire power grid, so the voltages such as the 161 kV until 765 kV. So there could be 1,000 kV in China or 800 kV in other countries. So when we want to utilize electricity from a transmission system, we need to take electricity from a transmission substation. And first, we need to decrease the voltage to a level lower than transmission. Typically, it's lower 138 kV, from 35 to 138 kV. So that part of system is called sub-transmission system. So this part is just to connect transmission system to diffusion system. The diffusion system will operate at lower than 35 kV, and it will gradually decrease the voltage to a low level to feeders and to send electricity to buildings, to homes. Okay, so I will stop here to answer any questions you have. Is there any question?